Thanks again, everyone, for joining us. My name is Rob Morris, and I'm going to be speaking today about using Wolfram Alpha in the physics classroom. I've taught physics for a few years at the college level, and so I have some experience with this and some ideas I wanted to share with everyone that I've used in my own classrooms. Okay, so to get started, I want to just briefly talk about what is Wolfram Alpha. This presentation is part of a series of using Wolfram Alpha in different classrooms, so we don't expect anyone to have any background with Alpha, though I know a lot of you have used Alpha and other Wolfram language products before. So what is Alpha? We call it a knowledge-based computational engine. The idea behind it is that it's built on lots and lots of data, and you can give it natural language queries, and these will draw on the data, understand understand things about the data, like what type it is, and do computations on it. So I can ask it questions like, what's the largest company in the US? So then it'll look through all of the known companies, and then it'll say, what do you mean by largest? It'll make a guess, and then it'll find all the ones in the US, and it will return a result. So it's not just looking up answers. It's not a search engine result. It's doing computation based on what you're asking for. You can find Wolfram Alpha either through the website, that's the most popular. You can get it on different mobile apps. If you like it, you can make it a browser toolbar and just access it that way. We always like to say that Wolfram Alpha is built on the Wolfram language. Many of you are probably familiar with Mathematica, which is another product built on the Wolfram language. It uses the Wolfram language. So Wolfram Alpha is a great example of a large enterprise scale product you can make using the Wolfram language. And like I said, it's got just a collection of lots and lots of data. Part of that is known physical equations, useful for physics and chemistry and lots of other things. I'll show you a lot about how those equations can be used in the classroom. So just thinking about how Alpha could be good for a physics classroom, let's go to the physics examples page. This is if you go to Alpha and you click on examples, you can get to a physics examples page. This notebook, this slideshow that I'm using will be available for everyone. So all these links will be available to download. You don't need to worry about copying them down. So in this physics examples page, it's a broad overview of lots of different subject areas that you might find Alpha useful for. So there's mechanics, quantum, statistical, particle. There's a whole range here. Everything from very elementary, mechanics, Newton's second type problems, all the way up to particles and astrophysics. You can ask it for the Lagrangian of a three-dimensional harmonic oscillator. It really runs the whole gamut for physics. Some of the things that I think are particularly useful, especially in the high school level, are the mechanics examples. So looking through, you could do a lot of kinematics and dynamics. We'll talk about some of these specifically, but like I said, you can do all the way up to sort of advanced classical. There's electrostatics as well, lots of stuff like that. I know students are interested in things like quantum mechanics and quantum systems, so it's also a good resource for them to sort of play around just to sate their curiosity. If they want to know more about the EPR paradox or something like that. There's also a large collection of just information available. Rather than going to search engines, looking up in books or anything, we've curated this data. It's citable, so if you want to know, the value of the Bohr magneton, we'll give you a reference. Unlike a lot of search engines, you can go and actually figure out where the data came from. So it's a good sort of one-stop shop for your physics needs. So I would be really remiss if I didn't talk about step-by-step solutions in the context of the physics classroom. So step-by-step is one of the few things that I will mention today that requires a paid pro account. But it's so useful, and students, it's one of the main drivers for students picking up pro accounts, or for teachers to pick up pro accounts. So I do want to talk about it. Basically, a lot of problems that are built into alpha, it has equations that it knows for different problems. So I could ask it for the escape velocity of a 3.2 Earth mass planet. Well, it knows the escape velocity equation, and it knows how to solve equations, and it knows how to generate step-by-step solutions for solving equations. So you can get a step-by-step solution to solving this physical equation. So to solve this escape velocity equation problem, it first says, okay, what is the information that I know? What are you putting into the problem? And notice that, I said Earth mass planet. Well, it assumed then that I'm going to use the radius of the Earth as well. So it's a little, it does think a little. So going through, it tells you to convert everything into the right units, plug into the equation appropriately, and I'll show you how to solve the equation and so on. So this, for many, many, many types of physics problems, there are built-in step-by-step solutions. These are just a few. This is finding the orbital period using Kepler's third law. And I want to point out, the syntax for this query. I just said Kepler's third law with 4 solar masses, 5 Earth masses, and it knows, it figures out based on these laws what the different inputs should be, and it'll walk you through. So again, it'll just give you all the steps to the problem. So this is a very valuable resource. I don't want to pitch too much for the pro plans, but it is a really useful resource for you and your students. Here's photon energy. It's a very simple equation. You get the picture there. So how can I use the freely available Wolfram Alpha in the physics classroom? There are a few different ways that I want to talk about. They all have a central theme that I will try to elucidate. But the first major way I want to talk about is using data. Like I said, alpha is built on data, so it knows lots and lots of things. And just by using that, you can give your students a place to sort of play around with. One example I like is with work functions. So you can look up, say, the work function of aluminum. And it'll say, here's the result. Notice that it's a range. And that means that the threshold frequency is a range. Anytime that you give your students license to just start exploring, and you give them resources to go play around and find out about the physical world, you're going to run into physically interesting, critical thinking questions. Like, why is there a range? Why is there a range in the energy and in the frequency? Just asking them these simple questions makes them think beyond the sort of rote problems they often encounter. But what I like to do is to pair this with known information about aluminum. So again, we have a huge data repository here. So I can look up the work function for aluminum. I can find a range of values, find the median value, and then I can associate that with just known information about aluminum. So I look up aluminum, and it's got all of this physical information available, like the melting point, boiling point, thermal conductivity, all these things. And so you can give your students license to just go explore and say, find a variable or find a physical property that has some sort of mathematical correlation with the work function. So they go and they look at work functions of different elements. They look at the different elements and maybe they pick Young's modulus. And so they graph work function versus Young's modulus. And maybe they see a relationship, maybe they don't. Maybe somebody picks Young's modulus and they see a relationship, and somebody picks speed of sound and they also see a relationship. Then you get to ask the question, well, is the speed of sound related to the Young's modulus? These kinds of things. I think that one of the biggest hurdles that my students would face is that they felt like the physics classroom was so rigid and so rote. And if you deviated from the path, you were in some way failing. And that's so antithetical to the way that we do science. So why not give them the resources to do science from the beginning and just say, here's a bunch of data. It's as if you measured the speed of sound. You can just go ask questions about different materials and see if they correlate. So I think there's nothing wrong in just sort of mining the data that's already out there for pedagogical purposes. Another type of known data is measured absorption of electromagnetic waves. So you could look up the absorption of EM waves, let's say at a given temperature and a given humidity. So it's assuming that it's in air, obviously. And again, note the sort of simple natural language query that I've made. Absorption of EM waves at a temperature and humidity. That in and of itself is also a good question. Having your students try to find these answers, they need to realize that humidity is an important part of the question. I need to ask the right question in order to get a proper answer. So looking at the data, you can see at this temperature and humidity, this is the attenuation curve. And it's interesting, you can ask your students, okay, well, given this attenuation curve, wherever it came from, we assume that somebody measured it well, and that's fine. What do these bumps mean? How could you interpret this? And you can ask them to change it. Maybe I want to look at higher pressure. So I'm going to double the atmospheric pressure. What happens to the attenuation curve? You can see that first bump changed significantly. So now you get to ask them all sorts of fun questions like, why would there be a bump in the attenuation curve? And why would that bump depend on atmospheric pressure? Things like that. So just giving them known data and having them play around with it and just asking them to think about why things might be, explain in their own words. It really moves away from that sort of shut up and calculate mindset that we often pigeonhole our physics students into. And then this one I just like, this for my own personal pleasures, I guess. I would get bored with my Archimedes principle problems, and I would want to find densities of very, just varied objects, and I wanted to sort of spice up my physics classroom. So I like using something like the density of wood calculator for an Archimedean principle problem. And so you can say, what's the density of oak? And then you could say, what's the density of all these different trees? There's something about relating it to very specific objects that I think makes physics more personable to your students. I had a lot of students react to, say, kinetic friction coefficients, static friction coefficients, when they get to look up these tables of, oh, this is, a certain type of material at a certain temperature and everything. It makes them realize that it's very physical. They spend so much time thinking about abstract, blocks on abstract planes that it's good to root them back into the real world. At the same time, though, you could sort of trick them into understanding things better when you get to have specific real-world data. For instance, give them the densities of all the known trees, and then ask them, okay, well, of those, if I had a 3 kilogram block of each of these trees, which one would float the most? What if I had a 4 kilogram block? What if we did it in terms of the shape of the block instead? Make them realize that it's just dependent on the density. It doesn't depend on any other physical properties of the wood, even though we have all of these properties available to us. So that's one way you can use Wolfram Alpha, is just to play on the data that's built in. Another way is to use the built-in equations. Like I showed you, we have different equations that you can get step-by-step answers from. One of the, I think, most translational skills from a physics classroom is being able to model a physical scenario, being able to argue quantitatively what might happen in a certain scenario. So, for instance, let's take a common problem, the Venturi tube. So I just query Venturi flow meter, and I get a nice little calculator here that will determine the flow rate. It's got a nice little diagram, and it sort of corresponds nicely to what you see in your textbooks. What doesn't correspond nicely, though, is this equation. The Venturi flow tube is often something that we do in multiple steps, because each individual step is pretty easy to understand on its own. But rarely do our students combine all those steps into one big sort of closed form. And so asking them, giving them this closed form equation, and asking them things like, what happens if I change D2? How is Q affected if I change D1? It's a skill in and of itself to be able to understand both mathematically what happens and from a physical intuition what happens. Because looking at such a complicated equation, but a simple physical scenario, their intuition and their mathematical intuition are going to be at odds. It's going to be easy for them to say, oh, if D2 increases, then the flow this flow speed will decrease. But looking at this equation, that's not so obvious. So giving them scenarios where their physical intuition can help build their mathematical intuition, it allows them to sort of isolate those muscles, which I think are some of the more useful muscles that you develop in a physics classroom. There are some more examples of this that I think are fun. This one I like because the equation is kind of complicated, and the physical system is simple. If you think about elastic collisions, the physical system there is also pretty simple. If I hit something at the same speed with more mass, then it's going to impart more momentum. It's sort of easy to understand. The reason I like focusing on these closed form equations, though, is specifically because of the subscripts. Nowhere else in my physics classroom did I yell more at my students about using proper subscripts and being very pedantic about labeling and everything. These equations for the final velocity in an elastic collision, they're labeled nicely, they're labeled neatly, and having those labels kind of obfuscates the equation itself. And so I think that that's a good skill for students to specifically drill in on, is given an equation that has some sort of complicated looking notation, can you pick through the notation and get to the meat of it and really understand what's going on if I change M1 or M2 or something like that. This one is the classical rocket equation. So it's the momentum transfer equation if you shoot out rocket fuel. I like this one because, one, it's rockets. Who doesn't like rockets? And two, this is where you start to move into the more applicable side of this skill. You've practiced this skill by looking at complicated equations or messy equations, and you're able to read them and see them. But now I want to know, why would you expect this log to be here? why is this the ratio of M initial over M final? This is where you start challenging your students to think about the physical scenario and make an argument about why the equation makes sense. I feel like we derive from first principles a lot, or from our sort of physical axioms. But in taking this outside of the physics classroom, we spend a lot of time in the real world just sort of making an argument about how things might be quantified. What the relationship between this quantity and that quantity might be. And so I think that that's where this is a good skill. This is where you take something that they may not have studied. They may not have derived the rocket equation. But if you make them sit down and think about, why is this log? Where is that coming from? Where do you normally see log? Then they can understand better how to apply that to other scenarios. Oh, that was my last example. There's in the presentation you'll see a Sackur-Tetrode equation. It's also another just hairy, complicated equation that if you want them to practice, what happens when I change this quantity or that quantity, it's a good example of that. Okay, so we've looked at using data, and we've looked at using equations that are built in. Now I want to talk about something that I consider to be a little more foundational. It's a little more substantive, which is the built-in calculators that are in Wolfram Alpha. And there are two major points that I want to make about these. The first is that when I spent time looking at what my students were actually doing in class, when I gave them a problem set, how much time was spent doing the setting up the problem and how much time was spent doing the algebra. Or as I was going through my lectures, how much time was spent doing algebra on the board and how much time was spent talking about the problems. I was dismayed at how much time I spent just doing algebra. And I think if you had somebody come in and look at your classroom, there's a good chance that they would think you're teaching a math class, because your students spend so much time practicing skills that they ostensibly should have learned, a year or 2 or 5 ago. So as we introduce computers into the classroom, one of the things we can do is to offload those skills. I'm not saying that all of my students could do algebra, perfectly. That's clearly not the case. But I want to make sure that I'm not just focusing on those math skills when they're in my physics class. So we can use calculators to sort of push past that. One of the examples I like is with moment of inertia. I had a lot of students who, we would get to rotational motion, they wouldn't understand that moment of inertia, sort of just like mass, was a number. They thought it was a big, hairy, complex thing. And even worse, they thought it was an equation, because it had an equation. I could calculate it. And they thought that things you could calculate were not just numbers for some reason. They didn't make the connection that at the end of the day, you can use an equation to get a number, but then that's all it is. It's just a property. So having a thing like a moment of inertia calculator, I think it allows you to really force that into them, to have them calculate lots and lots of moment of inertias without having to worry about integrating or doing the algebra or anything. So I could do, let's say, moment of inertia of a cone, or disks and cuboids, elliptical laminas, all these things. Another thing that this emphasizes is students think that you can only calculate the things that you're exposed to. Students will see moment of inertia for, cylinders, or for points, or for thin disks. But, so they think that the moment of inertia of like an elliptical lamina or a triangular plate is not a thing, because they've never seen an equation for it. And that's because the equation is probably too hard for them. But that's the wrong message to send. We want to make sure that they know that it's just a number. It's just, it may be difficult to calculate, but it's just some number. It's a property of the object. And so, even though they may not know the math that goes into it, there's nothing wrong with them finding the moment of inertia of a triangular plate or something like that. And then once you have that, let's say, we calculate this. Once you have that, then you can just, oh no, it's coming, never mind. So here's my moment of inertia, 107.78. Then I can take that and say, plug it into a rolling motion calculator. So, these are in different units, but that's okay. I'll just change this to gram meter squared, 778. So, giving them the tools to do these problems over and over and over again quickly, just by using the calculator, I think that it allows them to understand that there's no grand mystery to them. They're not exceptionally difficult problems. They're no more difficult than finding cube roots or square roots. That's something that we traditionally offload to calculators and we don't think twice about. So giving them this sense of safety of, oh, I can just calculate it and it's fine, I think really shows them how easy these things are. So I think another role of calculators, though, is to do what I call computational experiments. And the point of these is that during the physics class, I think that taking time to do the physical experiments of, say, dropping something and timing it, or doing the push carts and looking at the change in momentum and stuff like that. These are great skills to have, and I wholeheartedly think that we need to do that in the classroom too. But again, I think the most translational skill that you can bring out of the classroom is the ability to analyze the scenario. I can walk out of a physics classroom and I can go to a bank and help them analyze their finances. But not many people are asking me to drop a ball through a light gate. So we need to make sure that we're playing up the analytical part, the numerical, quantitative part. And to do that, we need to cut out a lot of the time that we spend doing the physical experimentation part. Because I think, if we're honest, a lot of the classroom time is spent just sort of watching our lab partner do some repetitive motion. And that's not helpful. So we can use calculators to offload a lot of this for us. So one I like is the time to fall calculator. So this one just is what you expect it to be. How long does it take to fall a certain distance? So how I would use this in the classroom is I would put in different distances. I would make my students maybe pair up and then put in different distances, and then look at the time to fall and the final speeds. And then do that for lots of different inputs. And look at all that data and try to analyze it. How does the time to fall, how is it related to the fall distance? Is it quadratic? Is it linear? Does it have a relationship? How's the final speed related? You can do this before you ever try to derive Newton's equations or kinematic equations or anything like that. It gives them a sense that the real world follows equations just like the computer does. I think it's sort of, unfortunately, it's easier for students to realize that when I put in a different number, the computer has a formula built in that it is using to compute the time it took and the final speed. What I think is difficult for students to realize is that when I drop a ball from 120 feet, the universe also has these built-in systems, and the time to fall and the final speed are also governed by equations. So it's I think easier for them to figure out that the input and output are connected mathematically when they look at it through a computer than they do when they look at it just through physical experiments. Now, this doesn't mean that you shouldn't do the physical experiment, but I think you should do it before the physical experiment. And then when you do the physical experiment, they'll get noisy data, and they'll realize the role of physical experimentation and error in the whole process of the scientific method. By doing the experiment, they're going to not get these nice clean curves, which you might get if you just sort of knew the answer. And this one is fairly easy to do. We can drop things off of stairwells and time them and stuff like that. But there are a lot of things that we can't do, or maybe we shouldn't do in real life, like drop off tons and tons of nuclear bombs. So I could look at a nuclear explosion calculator, and I could put in different yields of a nuclear bomb, and I can get all of these properties, like how high would the cloud be? What's the blast radius? And to be honest, I don't know. This isn't my field. I don't know how these things are correlated. So when I put in 2 megatons, I don't know how the blast radius is going to change in proportion. Not linear, sublinear. So, as just a person who's interested in the world, I want to put in different yields, and I want to look at different blast radii, and I want to graph them, and I want to see what the mathematical relationship is. And that's a perfectly legit thing to do, and it's, fundamentally it's not so different than, sort of doing the experiment itself. It's just it's much less destructive and expensive. Another example of this is asteroid impact. You can't call down asteroids from the sky at will, so it's difficult to know, let's say, what the debris field diameter is going to be just by doing the experiment. So we have the computational experiment that we can do. I can put in different initial velocities of the asteroid, and then I can see how the debris field diameter changes. And so I can take data from these computational experiments to then analyze and understand. And the idea here is that it's interesting. It's not something that they can do, they have access to. It's based on real-world known data. We're not just making this data up. So it is rooted in reality at some point. But it really drills down on the skills that make them quantify systems and understand relationships between quantities. This one is outside of my field. This one's a little more engineering physics, but anyone that's interested in like beam deformation or load on different types of levers and so on, there's a very robust calculator for that. It's got nice graphics and everything. You can change the support type. You can change how you put the load on and things like that. So if engineering type physics is more your purview, then this is an interesting calculator for you. So those are the 3 major parts of alpha that I think are useful in the classroom, just using the sort of built-in data and the built-in equations and so on. I think that there's a lot of fodder for activities and so on. And the overall theme here is that you can use the built-in data and the calculators and so on to do things that you can't easily do in the classroom. And you can do them over and over and over again so that your students understand that there's no magic or mystery in the process of, say, calculating something or measuring something. At the end of the day, they're just trying to get data, and they're trying to analyze it. There are other Wolfram Alpha features that I want to talk about. I mentioned step-by-step as part of Pro. Pro and Pro Premium are paid plans. With those, you get higher computational limits, so you can do longer computations. You can upload data sets that you or your students create, and will automatically analyze them and do statistics on them automatically. Clearly, step-by-step solutions are a big draw. web apps are a new thing that we have introduced recently, and they're sort of form-based calculators for different things. There's a lot of math and science class coverage in the educational collection. In the personal collection, you can do things like figure out how many calories are in a meal, or how long you can stay in the sun with a certain sunblock, and all kinds of just neat things that are built into Alpha that we've sort of exposed better. One thing that's very interesting, again in the context of make sure you're a physics class, not a math class, is the problem generator. So the Wolfram problem generator is now free to use, which means that your students can practice problems for free. The things that are not free are going to be the step-by-step solutions and generating quizzes. But so you can send your students here, and if they're having an issue with certain types of problems, and you can identify that it's the math that's giving them trouble, well, send them to the problem generator and make them practice something like this. So I could say, do this on the fly, 8 square root of 5. Let's try this. Oh, not correct. Oh, that's because it's 7. This is what happens when I try to think and present. So you'll see that you can practice for free. It'll keep a history of what you've done. If you are having difficulty and you have a pro subscription, you can get the step-by-step solutions. If you want to generate just random problem sets of a certain type for your class, you can do that with a pro account as well. So the problem generator is a great way to just hone the skills that are lacking for certain students. Another thing we really like is we just launched an add-on for Google Drive for Wolfram Alpha. So if your students use Google Docs or Google Sheets, if you use them, you have a few ways to use Alpha inside them now. It's a free add-on. You can go to this page and you can download them by clicking on these buttons. And you can do two things. You can bring up a sidebar in Docs and Sheets, and that way if they're doing, say, a lab report and they need a diagram, we have like, say, a good block on a hill diagram, then they can pull up the sidebar, query block on a hill, and they can drag in the image, things like that. If they're looking for physical constants, anything like that, they can pull up the sidebar and just query them and get the information. You can also just type in what you want to know and highlight it and click on Compute Selection with Wolfram Alpha, and it'll just replace it. So here it's an example of population of Greece. I hit Compute Selection and it just replaces it. So I could say, I could do something like the speed of light in a vacuum, and then just highlight and replace. It simplifies the workflow for creating lab reports and so on. So those are all the features that I wanted to mention that I think are useful in the classroom for Wolfram Alpha. If you want to get started, but you want to, what I want to say, if you want to get started and you want to, say, get a few licenses for your class or for your school or something like that, you should contact us about our grant program. This is for people that are sort of concerned about the expenses involved. We have grants that we can give that knock down the price significantly. Just contact us at education-support@wolfram.com. Contact us through the Q&A right now, and we can talk to you more about getting that. The price shouldn't be a concern if you want step-by-step for all of your students or something like that.